Hello and welcome to day 2 of Video at Scale 2023. My name is Shinjan Tiwari and I will be your host again for today. Yesterday, we focused on system aspects of large scale systems that handle media. It included components from server and client. Today, we will focus on the technological and algorithmic advancements in the field. We will feature presentations from Eluvio, Google, Heygen, and Meta. Like yesterday, we will have an opportunity to ask live questions to these experts. As a reminder, all presentations and live Q&A sessions will be posted to the AtScale conference website, AtScale Facebook page, as well as the AtScale YouTube page following the event. We will close the event with a live panel discussion talking more about building at-scale video infrastructure anywhere. Now, I would like to introduce Nicole Kwa from Google. Nicole has worked at Google for over 8 years and manages the engineering team responsible for live ingestion at YouTube. Nicole would dive deeper into a streaming protocol so ubiquitous when it comes to live streaming and why it might need a refresh. Welcome, Nicole Kwa.
Hi all, my name is Nicole, and I hail from the world of YouTube Live, where we work on the infrastructure that supports live streaming at YouTube. This includes both what you might think of as regular YouTube and actually also YouTube TV. Today, I'm going to be telling you the story of enhancing RTMP. This is an effort that many were involved in, but I will tell it from the perspective of our involvement as YouTube Live. Alright, so first off, let's level set a bit. Where does the story of YouTube Live start? The very first incarnation of YouTube Live was actually back in 2008. In terms of a few early highlights, in 2012, the London Olympics were live streamed through YouTube. Maybe some of you might remember the Red Bull Stratos event, where an Austrian skydiver jumped from the stratosphere. This jump lasted about 10 minutes and was watched by over 8 million concurrent viewers on YouTube back in 2012. So over the years since then, we have focused on our side on scaling the platform and the infrastructure, and bringing new capabilities to creators across a variety of settings. And when I say a variety of settings, it really spans the whole gamut. We want to enable creators to engage in, laid-back, casual conversation from their mobile phones. And on the extreme other end of the spectrum, we also want to enable professional broadcasters, the workflows of ESPN and ABC and the like. But here at YouTube Live, we also challenge ourselves to enable regular creators to create high-quality streams. We are talking here about streaming in 2K, 4K, HDR, even if you are not a professional TV-style broadcaster, and even if you don't have high upload internet speeds at home. This was the driving goal that led us down the road of enhancing RTMP. Since not all of you may work with live video, I wanted to take a quick moment to point out how the live streaming setup differs from VOD, or video on demand. Live input can come from a variety of different devices. Your camera, your computer screen, but the key thing is that an encoder is always involved to send media data to the server via an ingestion protocol. Now, the protocol used for the ingest step does not need to be the same as the one used to deliver media to the players. In fact, most of the time, they are not the same. And as you can imagine, different protocols have different pros and cons when being used for ingest. So going back to the evolution of YouTube Live, we added different ingestion protocols along the way in order to support the wide variety of use cases on our platform that I explained above. We actually started off with RTMP as our first ingestion protocol. Later in 2017, we added WebRTC to support creators live streaming from their mobile phones. In 2019, we then added HLS support. This enabled us to be the first major platform to bring HDR live streaming to creators. And also, for creators who wanted to use more modern codecs like H.265, we recommended that they send their streams to us via HLS. Now, accepting H.265 meant that creators could send us higher quality, talking like 2K, 4K content at much lower bit rates compared to H.264. This benefits creators with low bandwidth connections And we really hoped that it would open up high-quality, high-resolution content to be accessible to more people in terms of creating the content. But as I mentioned, ingestion protocols have pros and cons. HLS has some downsides. It's a high-latency protocol, and because it's chunk-based, it can reduce ingestion reliability under poorer network conditions. But most importantly, although it is used heavily for delivery, it's actually not widely available in the encoder ecosystem for ingestion. So we wanted to make creating high-quality content at lower bit rates accessible to creators, but HLS didn't really solve our problem. This led us to sit down and ask ourselves, can we do better in the near term? RTMP is still widely available, and it's widely used for ingestion. It looks like it will be a while before all of this changes. So, as YouTube, is there something we could do for the ecosystem so that we can meet creators where they are at? All right, so we've talked a little bit about YouTube Live and how we got to a key decision point about what we wanted to do about RTMP. Let's backtrack a little and talk about RTMP. RTMP was developed by Macromedia, and it made its first appearance all the way back in 2002 with the launch of Flash Player 6. In the 2000s, Flash, some of you might remember, was very popular. And so you can imagine that RTMP was heavily used to transport media over the internet. During these years, more platforms also started to accept media via RTMP. And so there was an explosion in tooling and encoder support for RTMP in general. However, today, Flash is officially deprecated, in fact. Its end of life was announced in 2020. So RTMP is basically no longer used for delivery. It's been replaced by HTTP protocols like HLS and Dash. However, because of that explosion of tooling and encoder support back in the 2000s, RTMP remains incredibly popular among the vast majority of streamers for ingestion. In terms of maintenance, Adobe publicly released part of the RTMP spec in 2012, but it has not updated it since then. In 2019, they licensed out the use of RTMP software tools to a company called Veriscope. This is where the story continues. In 2021, YouTube then gets in touch with Veriscope and starts discussing various options to be able to get the RTMP spec updated. Veriscope then reaches out to Slavic, pictured here. Slavic was actually a core member of the team that originally developed RTMP while at Macromedia back around 2000. And funnily enough, Slavic's first reaction was actually surprise. Mild shock, pleasant surprise though. He said he almost couldn't believe that 2 decades later, RTMP continues to be so popular and so highly used. The next step after this is, in 2022, Viovera Software Organization gets founded as a non-profit foundation. Slavic serves as the chairman of Viovera, and the goal of this foundation is to help update the RTMP spec for the benefit of the wider community. Now I'll take a moment to explain a couple things. We usually say we're enhancing RTMP, but to be precise, we're actually also enhancing FLV. Let me explain. So RTMP messages have this message header that you see. This message header is followed by a message payload. Messages can carry metadata, they can carry commands, control messages for communication between the client and the server, they can carry synchronization objects, and of course, they can carry media data. But note that RTMP itself, in the spec, does not actually constrain the media data in the payload. What happens is that RTMP actually leverages Flash Video, aka the FLV container format, for media. Just in case anybody's not familiar, FLV is a fairly lightweight container format. It comprises alternating tags and backpointers. There are 3 types of tags: video tags, audio tags, and script tags for metadata. Each video tag typically contains 1 frame of video. Backpointers specify the size of the preceding tag. In terms of structure, tags, as you can imagine, also have a header and a data payload. But you'll notice that the structure of the RTMP message header actually matches the FLV tag header. You'll also notice that the RTMP message header has a message type ID, and the FLV tag header has a tag type ID. These ID values actually intentionally match between RTMP and FLV for video, audio, and any script metadata when it's encoded by AMF0. Hopefully that makes it clearer then, that when we say that RTMP needs to support more modern video codecs, we actually implicitly mean that FLV, the FLV spec, needs to be updated to support more modern video codecs. So how did we add these additional video codecs? In the original FLV video tag header, the codec ID is specified as 4 bits. Of course, since it's 4 bits, there's a maximum of 15 values. 7 codecs were originally defined. So, as you can imagine, the easiest solution, of course, here is to simply extend the codec IDs up to a maximum of 15. And to start off with, we were prioritizing 3 codecs, AV1, H.265, and VP9. So, of course, we have 8 more values to play with. This should work fine. But the enhancement actually takes a more future-proof approach. It actually provides a mechanism to signal that an extended video header format should be used instead. Within this extended video header, new codecs are specified as 4-character codes, which obviously removes the restriction of having just, 8 more codecs that you can play with, and after that, you're done. Also, by specifying a new extended header format, this provides additional flexibility for, any future changes where you need to possibly provide finer levels of metadata. So we added that, and then the second enhancement that was added was actually to support HDR. Within that same extended header that I mentioned just now, you can specify different packet types. And there was a new packet type called metadata, which was added. Within this metadata packet type, which I know is a fairly generic name, you actually write an AMF string called color info, and after that you write an AMF object. Within the AMF object, you can encode basic properties like color primaries and transfer characteristics, which are important for carrying HDR-related metadata. And you can also encode more advanced properties like minimum and maximum luminance. One thing I wanted to emphasize, while they try to be forward-looking, the enhancements to RTMP and FLV are always backwards compatible with the previous specifications. As an example of a trickier case, here's how the enhancement spec signals to use an extended video header. So actually, from the first 4 bits of the original video tag header, the enhancement says to use the most significant bit of those 4 bits as a Boolean to indicate whether or not an extended header is being used. But the spec is very careful because it ensures that this single bit that's now being used as a Boolean was previously always 0, and therefore is safe to now use in a backwards compatible manner. All right, so I explained, at a high level what the changes were that were included in the enhancement spec. And in the scheme of things, these are not very complicated changes. That's actually important because we do want the changes to be a light lift for the ecosystem to adopt. And yet, behind the scenes, actually a lot of feedback was involved to bring these enhancements to life. I mentioned Beamr just now. So Beamr's software organization actually formally includes Adobe, YouTube, and Twitch as members and sponsors to help update the RTMP spec. But we also had a lot of valuable input from experts both within Google and, importantly, outside of Google. There were many more partners and representatives from across the industry who were involved in critically shaping the spec. This also includes core members of communities like OBS and FFmpeg, and they could provide their expertise and their perspectives from the open source world. And I'll also give a call out that one of the original editors of the RTMP spec from 2012 was also involved in providing critical feedback. Finally, what happens? In March 2023, Beamr publishes the first enhanced RTMP spec on GitHub as a public beta. This is a huge milestone because it's the first formal Adobe endorsed update to RTMP's capabilities in over 10 years. Great. So, where are we now? I mentioned earlier that our original objective at YouTube was to see if we could enable creators to send us higher quality streams at lower bit rates while using the workflows and encoders that they were already used to. And the spec enhancement that I just said was published back in March includes support for HDR, and it does include support for the additional video codecs AV1, H.265, and VP9. These are all much more efficient codecs compared to H.264. But in particular, here at YouTube, we were excited about supporting AV1. Scratch that. We were actually extremely excited about AV1. As most of you know, unlike H.265, AV1 is royalty-free, and this makes it extremely attractive for adoption. The AV1 spec was released in 2018, and pretty much since then, we have been excited about it as the way of the future for live streaming. But before we could start accepting it for live, the ecosystem actually had to catch up. In particular, software encoders for AV1 tend to be slow. But for live, obviously this doesn't work because for encoding, you have to keep up in real time. And so what happens? At the end of 2022, the major GPU vendors all have released their first series of cards that support real-time AV1 encoding. And so the pieces are now starting to fall into place. With the advent of these new series of GPUs, YouTube can start accepting AV1. So shortly after Beamr publishes the enhanced RTMP spec, YouTube releases support for AV1 and H.265 ingest over RTMP. For this, we worked really closely with the incredible OBS community to bring this capability to creators. And just to give you an idea of why we are so excited about bringing this to creators, here's an example of us playing Forza, which is a racing game. Yes, we do play video games at work. This first screenshot is taken at 4K, 60 frames per second, and it's 10 megabit per second bitrate. And it's a racing game, so it's high motion content. And I want you to look at the sky, look at the grass, look at the buildings on the left and the radio tower on the right, and you can see how blocky everything is. And there's lots of encoding artifacts and lots of detail. Now here, this next screenshot is the same frame. It's encoded with AV1, also at 10 megabits per second. And you can see the incredible increase in detail. There's much less evidence of compression artifacts. I'll take this chance to emphasize that, yes, YouTube Live does transcode live streams, but a better quality at ingestion still means that the output is going to look visually better too. Speaking about AV1 just in general, here at YouTube Live, we are at the vanguard of helping to grow and develop this new emerging part of the ecosystem, and we actually strongly hope that other platforms will be able to support this capability soon too, to further spur the growth of the AV1 ecosystem. All right, now, taking a step back. We started off asking ourselves, back in 2021, if we could do our part to move the ecosystem so that creators could send us higher quality streams at lower bit rates using their existing RTMP workflows. And as you can see, in 2023, we did it. But fret not, the story continues. So right now, we are working on getting these changes adopted. In fact, thanks to Jean-Baptiste from FFmpeg and his great team, the video codec extensions are already available in FFmpeg Head for anybody who wants to play with them. And also to give you a special sneak peek, there are new features being worked on for the next version of the spec. These include modern audio codec extensions. We did the video codec extension, so we do also want to extend it for audio. It actually includes multi-track video and audio, and functionality for reconnection. Longer term, we also have representatives on our side involved in shaping a new IETF standard called Media over QUIC, and we hope that this will replace RTMP in the further future. To wrap up, I wanted to say a big thank you to the many experts and partners involved in making this happen. RTMP was launched in 2002, the spec was released in 2012, and finally here in 2023, we have the first set of new capabilities in over 10 years. This huge milestone would not have been possible without great collaboration across the industry and ecosystem. So thank you to all of you for making this happen. And we hope to also work with everyone to continue to bring more capabilities to creators soon. Wrapping up, I wanted to give a special call out and thank you to Colleen Henry from Meta and Alex Lindsay from Office Hours, who actually helped make introductions and bring people together behind the scenes to make this effort a reality. And also, thank you to Abhinav, the organizer of this conference. We hope that since you worked on RTMP back in the day at Macromedia, that this has actually been a great blast to the past for you. Thank you.
Thank you, Nicole. RTMP does remain a cornerstone of the streaming protocol for live streaming. But how about the guts of elementary streams? The very payload that contains the video bits? So much has happened in the field of compression, and the latest to make a buzz around is AV1. I will hand it off to Eric, who will talk more about AV1 in a conferencing setup. After the talk, Monica will lead a live Q&A session with Nicole and Eric. Keep your questions pouring in. Over to you, Eric.
Hi, my name is Yu Chen. I'm with the remote present video team in Meta. We work on improving video quality across the Meta family of apps. Today, I'm going to share our experience using AV1 to improve video quality for RTC at scale. AV1 is getting more and more popular in the video industry. Actually, Apple recently announced AV1 hardware decoder supported on their new devices. So it seems that adopting AV1 is getting more popular and becoming a trend, and this is favorable for RTC. Earlier this year, Nicholas from our team shared some initial results at the RTC at Scale event. Since then, we have hit several milestones and successfully launched AV1 on the Messenger app. There are more than 1 billion monthly active users on Messenger. This is a large scale, and including devices from desktop machine to mobile phones. Today, I'm going to share what we have learned through our development process. For people who may not be familiar with real-time communication or RTC, I'm going to start with a brief intro. The most popular use case of RTC is video calling. Unlike video on demand, the RTC has to deal with end-to-end video latency. Typically, we want to keep end-to-end latency to be less than 300 milliseconds. Once the latency goes over, the user starts to feel a delay. So it's always a struggle for RTC video coding system to provide high quality while maintain the latency low. In this case, we cannot do multipath encoding. The decoder side cannot do much buffering. Any bitrate overshoot would likely introduce a freeze on the code. And the RTC client has to do both real-time encoding and decoding. Both consume a lot of power. So lowering the power is critical, especially on mobile devices. So while we're interested in AV1 on RTC, let me show you some quality comparison between 264 and AV1. Here, we enable AV1 on Messenger app and have video call on 2 iPhones side by side. The bitrate is restricted to 100 kbps. AV1 is on the left, 264 is on the right. By the way, this is Roger, our manager. You can see that the 264 video is blurry and the AV1 video is visually better. This is a good example of the benefit of adopting AV1. We have seen the motivation for adopting AV1 on RTC. In the following slide, I'm going to share what we have learned through our development process. I'm going to share more results of AV1 in the first session. I will talk about the 3 important challenges we faced, including my favorite, which is increasing AV1 call coverage, as well as the solution we came up with. I will then talk about how we measure the impact on the product. Personally, I find this to be most interesting and most critical. Here are more detailed results of AV1 code on Messenger app. We have seen quality comparison under 100 kbps at the very beginning. If we further restrict the bitrate to 25 kbps, quality improvement is even more obvious. Low bandwidth network is an important scenario on Messenger app. This is especially true on mobile devices because we have to handle the poor network condition. The fact that AV1 gives very obvious quality improvement at low bitrate makes it a desirable codec for us. We have saw visual comparison. Let's look at the number. These are rate distortion curves. We usually use these to compare the coding efficiency of different codecs. The horizontal axis is bitrate, the vertical axis is PSNR. We encode a video at different bitrate. H.264 is lonely rate line. Other lines are different AV1 encoding preset. We use BD rate to measure the difference in comparison efficiency. From the top figure, we can see that under the same quality, AV1 saves about 30% bitrate, and under the same bitrate, AV1 can improve PSNR by 2 dB. Because AV1 offers screen sharing content coding tool support, in screen sharing scenario, the improvement that AV1 can provide is even more significant. We can see evidence in the bottom figure. Last but not least, we also observe improvement on user feedback in the A/B test for AV1 on Messenger. AV1 has several advantages for RTC. First, it offers better coding tool and so better compression efficiency and better video quality. I have shown you data to support this. And AV1 has RTC coding tool which enable encoder to be quickly adapt to the network during a call. This is critical. Two issues are important here: change in network bandwidth and packet loss. In order to handle change in bandwidth, the encoder has to adjust FPS and the resolution during the call. However, a change in resolution usually means that the encoder has to encode a new keyframe. This will introduce a bitrate spike and a video freeze. AV1 provides a new coding tool called Reference Picture Resampling or RPR to solve this problem. This tool allows encoder avoid encoding a new keyframe when resolution changes. Finally, there are several scenarios specific to real-time communication which we have to take care of. Screen sharing is an example. AV1 also comes with screen sharing coding tool support which can improve user experience. In our experience, parallel mode can effectively improve video quality by preserve sharp edge of text. Also, intra-block copy can significantly reduce screen sharing size. The fact that AV1 provides these two coding tool support as baseline profile is a huge plus. So I have shown the benefit of having AV1 on Messenger. Let's talk about 3 challenges and our solutions. Binary size was our first problem. For example, if we integrate liblm into Messenger, we will see an increase of 1.7 megabytes in binary size or 600 kilobytes after compression. An increase in binary size like this will lead to many issues. Update successful rate will be affected, so users would prefer not to update and keep using outdated version. Application start time would increase, and general software health metrics such as memory usage and crash rate would be affected as well. To give a rough idea, an increase in order of 600 kilobytes is a major problem and could mean a whole year feature budget for a large organization. We have a couple ways to mitigate the problem. First, we can use dynamic download framework to download AV1 as a separate feature component. Usually, this is our first go-to when we integrate a large library. However, the dynamic download framework is not perfect. In our experiment, we do see some download failure, perhaps due to bad network, device issue, or just some random failure. this will definitely affect user experience. So we prefer to reduce binary size instead of relying on dynamic downloading. We could optimize binary size. For example, quantization matrix is a coding tool in liblm. It takes up to 60K, which is about 10% of total library size. With optimization, it can be reduced to 30K. We can even go with the end-to-end pipeline optimization and remove unused coding tool from library. In the QN example, we can completely remove it and save 60K. At the app level, we also have a couple of options for optimization. For example, besides RTC, the app also has other features such as transcoding on video message. We can make some features share the same library to save binary size. Or we can make use of built-in codec support in a device instead of adding new codec library to the app. Our second problem is that AV1 adds significant computing complexity. This is not surprising. Even though the more advanced coding tool can enhance coding efficiency of AV1, it also requires more computing during encoding. The question then is, how this computation increase impact the app? In order to understand the power impact of AV1 computing, we measure the power consumption on a Pixel 7 during the AV1 code. We saw an increase of 0.1 to 0.3 watt when switching to AV1 encoding, which is 4% to 11% power increase. In addition to power consumption, memory usage increase is another issue. We observe a large memory usage increase on AV1 encoding compared with 264. This results in app crash regression, which I will explain in more details later. Since AV1 code needs more computing resources, the first thing we have to do is to identify the list of devices capable of using AV1. We don't want to cause video freeze or overheating when AV1 is mistakenly enabled on the ineligible devices. Having a list of eligible iPhone models was easy because there aren't many iPhone models. For Android device, it's more challenging. It's just too many legacy Android devices. We tried selecting device by memory, the year of release, and even the Android OS version. However, none of these strategies are reliable. In the end, we use Meta in-house device benchmarking system, and we are able to have a reliable list of Android devices. Our problem didn't stop there. We observed another issue from the A/B test, out-of-memory crashes. Initially, we suspect there may be memory leak in AV1 library, which was not the case after some investigation. There may be other background app causing the leak. However, with high memory usage, there is a higher chance of running out of memory and triggering the crash. Memory usage increase is correlated to video resolution. So to mitigate the regression, we design a codec switch mechanism. The AV1 is initially enabled only for low and medium resolution, and it fallback to 264 for high resolution. In fact, generally, hardware codec is preferred for high resolution because of power consumption. So before AV1 hardware codec support become available, we believe that is good strategy not to use AV1 for high resolution on mobile devices. So now we have solution for binary size, power consumption, and memory usage. We got positive result from the A/B test. We successfully launched AV1 on Messenger and make it available for high-end devices. On Messenger, we are covering about 60% iPhone models. For Android, however, the coverage is much less, at 15%. I will explain why. Even though we now have a list of all high-end Android devices, we found that a lot of factors could reduce the computing capability of these phones during the code. For example, if an app consumes a lot of power and running in the background causing device overheating, the device would have to reduce CPU frequency. To better understand the issue, this is the encoding latency based on the data we collected from the messenger. The distribution representing AV1 is more on the right, indicating higher latency compared with 264. We already expect that. What was surprising was that the latency of some device was really close to the input frame rate. This means that this device is almost unable to do proper real-time encoding. In fact, in this case, this device would become hot and cannot encode AV1 video in real time. This results in video freeze. As a solution, we had to make our codec selection smarter. Besides resolution, we have to consider some device health measurement, such as encoding latency and even device battery level, to determine whether the device has enough computing power and whether it has to fall back to 264. With a more reliable codec selection strategy, we are able to increase Android device coverage by making AV1 available to mid-end devices. Some of these mid-end devices are not able to do real-time encoding, but they are able to do real-time decoding. In this case, we can use a symmetric codec design. mid-end devices would still encode and send 260 video, but they are receiving AV1 from the high-end device on the peer side. The way we have effective increase in AV1 coverage on Android devices. In an effort to continue improving code quality, we are working on this topic, encoding preset, rate control, and resolution tuning, and it's always worthwhile to improving encoding algorithm for quality improvement. When we ship a feature, how could we measure the impact become an important question. The measurement strategy has to not only provide evidence that the feature comes with many benefits, but also monitor the impact of feature in long term. So we need an in-product quality measurement. Currently, there's not a reliable quality measurement in the RTC pipeline. We simply don't have a good solution for this in the industry right now. I will use the WebRTC as an example. Its report resolution and the compression level, which is QP. This is more of a quality approximate. But if we want to compare two different codecs under the same code condition, in our case, AV1 versus 264, QP doesn't work. This is because different codec has different quantization definition, not to mention that each codec also has its own in-loop filter design. So we have to design our own quality measurement. It has to be low complexity so that it can cover all kinds of devices. In the field of video, PSNR is generally regarded as a reliable quality measurement. It does not require a lot of computing, but we have challenging if we want to implement the computation of PSNR in RTC pipeline. First, PSNR is a full reference matrix. However, in RTC video pipeline, the sender does not have decoded video. The receiver does not have original video. In other words, we cannot compute PSNR. Moreover, before encoding a video, a sender will scale the video according to bandwidth. This makes PSNR computation more challenging. To overcome these problems, we propose a framework for PSNR computation. We first modify the encoder, making the encoder report distortion caused by compression. Then we design a lightweight scaling distortion estimation algorithm. Based on the distortion value reported by encoder and the algorithm, a PSNR value is computed. With this system in place, now we could reliably measure the impact of AV1. There are more details to the design. For example, we observe a correlation between scaling distortion and encoding distortion, and we have to modify our algorithm accordingly. We are summarizing our findings and work, and will be submitting these to academic conferences. To sum up, we believe this is the right industry moment to adopt AV1 in RTC. In-product quality measurement is still a challenging issue in RTC product. We are looking forward to industry collaboration on this topic. Adopting AV1 also creates opportunity for metaverse applications. Some lessons we have learned could be potentially helpful to AV2. Finally, as we continue to improve AV1 code quality, an interesting direction is to use machine learning to solve some issue we encountering. This marks the end of my presentation. Thank you for your attention.
Hello, everyone. Welcome to the first Q&A session of today. I have with me our speakers, Nicole, Thomas, and Kirk from YouTube, and Yu Chen from Meta. Thanks for joining us. A quick note for everyone attending the event. Please do add your questions in the Q&A section on the events page. On that note, we have a few questions coming in, so let's just jump right into it. This first question is for you, Nicole. How early do you predict the RTMP to quick transition would happen? And a follow-up is, what are the challenges do you see in transitioning to quick?
Got it. And just, hi, everyone. I'm Nicole, and I want to take the chance to briefly introduce my teammates, Kirk and Thomas. And actually, Kirk will take this question.
Sure. So one of the things that we learned when we first introduced HDR was that we couldn't ask creators to change their workflow without a compelling reason. And this is the reason why when we decided we needed to introduce AV1, that we decided we had to find a way to update the RTMP spec. Therefore, the challenge of moving to a new standard like media over quick is making a compelling enough case that creators will want to move. So this is not just asking encoding vendors to make this switch to enable the functionality, but also asking creators to change their workflow. I do believe that it will be a slow process, but I think there's compelling enough reasons for us to be able to leverage better performance, better capabilities of Quick that ultimately the ecosystem will move. But as with most things in the ecosystem, it will take time. Did I get it all?
Awesome. Thank you. Thanks, Thomas. This next question is for you, Yu Chen. Did you combine the lib AOM power consumption metrics along with AV1 when used to make decisions on when and when not to use AV1?
Okay, hi, my name is Yu Chen. Currently, our codec switch currently on the power measurement we present, including both encoding and decoding. But on that power measurement test, actually we are using lib AOM decoding. So, and we haven't tested the AV1D yet, but we are interested in testing that.
Makes sense. Thanks for the answer, Yu Chen. This question is for you, Nicole. Thomas and Kirk, feel free to chime in as you see fit. What are your favorite and least favorite aspects of RTMP as a protocol?
I'm Thomas, and I'll answer this one. So my favorite part of the RTMP protocol is that it's a fairly straightforward protocol to implement. It's the sort of thing that an engineer can implement in a week or two without a lot of foreknowledge of stuff, which is part of, I think, the reason why it's been so successful in the industry. The thing I hate the most about RTMP, which is really, really deep down in it, is the way they handle extended timestamps. Everybody gets it wrong. and it doesn't make a lot of sense. But so that's my least favorite part of the spec.
It turns out one of the things I learned in video is time is hard.
Yeah.
That is true. Thank you so much. This next question is for you, Yuchen. Have you tested the AV1 hardware codec?
No, we haven't, but we are interested in testing Apple new released hardware decoder. This could help group code, especially on mobile devices. We are also hoping for hardware encoder support, but personally, I expect they may take some time, especially in our experience. The first release of hardware encoder is usually optimized for offline encoding, and it may take several iterations to optimize the encoder for RTC use case.
That is fair. Thank you. This next question is for you again, Nicole. Can you speak more to the upcoming changes planned or the changes that you would like to see in the enhanced RTMP?
Yes. So I can give a sneak preview of what's on the roadmap for next versions of the enhanced spec. I can't promise an exact timeline yet. So things that are in the works are actually audio codec extensions, because we've delivered on the video codec extension, so now we need to work on the audio part. The current ones include AC3, EAC3, Opus, and FLAC. There's also active work going on to support multi-track audio and multi-track video in RTMP. And we also want to support reconnect functionality. And we actually think this is pretty important, specifically the reconnect functionality for the ecosystem in general, and improving the smoothness and reliability of RTMP ingestions. Is there anything else you want to add to that, Thomas?
Yeah, I mean, the reconnection is really important in the modern system, where on the server side, we may need to update our services and break that connection. And it gives the encoder a chance to pick the right time for the connection to move to a new location.
Okay, a follow-up to that is, how long do you think patching RTMP will be sufficient for? And what are the benefits of the longer-term alternatives if RTMP continues to remain so popular?
So one of the challenges with RTMP is eventually it's based on TCP. So there's this head of line blocking challenge that occurs with RTMP. It's one of the reasons that we'd like to move to a QUIC-based system. If we make such a fundamental change to RTMP, it becomes a new standard. At that point, we might as well just look at a new standard altogether. I think ultimately these type of performance characteristics are going to be the thing that drive it. One of the reasons that we formed VioVera was because what we did not want is we did not want a meta version of RTMP, a Twitch version of RTMP, a YouTube version of RTMP. So we do strongly believe that standards are important. So we're working with the IETF on the media over QUIC standard with a number of industrial partners, so that we can come up with something that the industry can move to altogether. We think that standard, which is in process, in the works, feel free to get involved, is something that will be ready for publication, we hope, soon. And people can start working on implementation and adoption. So as with anything, it's hard to predict the future. As I said before, it's tough to get people to move, but we think that there's going to be enough quality improvements as well as new feature improvements to cause the ecosystem to move in that direction.
Sounds good. Thank you. This next question is for you, Yuchen. The PSNR measurement depends on the encoder to report encoding distortion. How do you feel with hardware encoders?
Hey, this is a good question. Currently, to support hardware encoder measurement, we have developed a a simple method to derive encoding distortion from QP. However, this is a short-term solution and not accurate for all video types. So we look forward to collaborating with the industry and the chip vendor to discuss the possibility of adding a distortion report on our encoder. And I also want to share that from our experience, the distortion before the loop filter is good enough. In other words, if the hardware pipeline already calculated distortion in the RDO process, it's good enough that we just report that distortion. In this case, we may not need additional complexity in those hardware encoder.
That makes sense. Thank you. This next question is for you as well. Given the increased compute and memory requirements, what was the impact on reliability and latency of the call with the rollout of AV1 codec? Did you have to make a trade-off to increase quality with AV1?
Okay, it depends. In the first few rounds of A/B test, we did see some regression in reliability metrics, such as crash rate and the battery, and some of them could be mitigated. As I mentioned in my presentation, we developed a codec switch mechanism to mitigate the crash regression. And as we keep improving our design, we do see more and more regression being mitigated. However, some of regression are side effects that we cannot avoid. Battery regression is a good example. And we know that there's a direct link between battery usage and the talk time. From our experience, increasing battery usage by 1% and the talk time will drop by almost the same amount. And luckily, the quality improved will also increase talk time, but we just need to find the right balance. So this balance could be the trade-off for increased quality with AV1, as you mentioned.
That sounds good. Thanks, Yuchen. This next question is for you, Nicole. What can you share with us so far about the enhanced RTMP adoption?
Good question. So there's actually two aspects to adoption. There's adoption by vendors, and then there's adoption and usage by creators. So in terms of vendors, we did mention that the functionality was released in OBS. And on our side, we are actively talking to or know of at least 4 other major encoders who have either implemented the new spec or are implementing it. We also want to mention that actually we're very happy about it, that FFmpeg 6.1 was released recently, and that contains the video codec extensions for enhanced RTMP. So any other encoder vendors who do actually rely on FFmpeg internally will be able to get that functionality by upgrading to 6.1. So that's on the encoder vendor side. On the creator side, so unfortunately I can't share exact numbers, but I can mention that HEVC usage through enhanced RTMP is strong on our channel, and it's vastly outpaced actually the HLS ingestion usage that we also support. And so that was one of our original goals, right? We wanted to increase accessibility to creators through exposing this functionality through RTMP and not just HLS, and we're seeing that pay out. For AV1 has the additional barrier where creators actually need to invest in and buy new GPUs. So of course that's adoption is always going to be a little bit slower, but we also see that climbing up into the right continuously. Yeah.
Great. FFmpeg adoption is great. Thanks, Nicole. And this next question is for you, Yuchen. What is the acceptable encoding latencies? And what are the resolutions you find feasible using software AV1?
Okay, the acceptable encoding latency depends on the application. So as I mentioned in my presentation, in typical video coding, we want to keep end-to-end latency less than 300 milliseconds. In that case, from several, like my local tests, I feel that like 10 millisecond encoding latency to 20 millisecond encoding latency is fair, but I also want to mention that there's some specific application looking for like extremely low latency, and in that case, like even like 10 millisecond encoding latency could be an issue. And so in short, like if the encoding latency requirement depends on the application, and then the resolution we can use AV1. It depends on the latency. And again, from my local test, I found that from the high-end device, the AV1 software encoding is feasible for at least for the resolution lower than 360p is okay, but we start seeing some issue on the resolution higher than 720p, especially on some mid-range devices. As a result, we need to design some codec switch mechanism.
Got it. Thank you. This next question is for you as well, Yuchen, again. Given the preconditions around enabling AV1, how do you foresee higher percentage of adoption of AV1? Does it need to depend on users migrating to high-end devices or devices with hardware support?
Okay. I can think of like three methods to that we can increase the AV1 coverage. The first, yes, as user migrate to high-end devices, AV1 coverage would be increased. And for sure, like hardware codec definitely help to offload the system overhead. In P2P code, the encoding is a bottleneck, and in group codes, the decoding becomes a bottleneck. So in group code, the hardware decoding is especially important. And finally, personally, I feel this is an interesting direction. We can define a ultra low complexity AV1 encoding preset, which has similar complexity to 264 encoder. With this new ultra low complexity preset, when the device does not have enough computing resource, it can keep using AV1 instead of falling back to 264. And in fact, the ultra low complexity preset may have slightly worse compression efficiency than 264 encoder because it has to disable a lot of complicated coding tool while still have low syntax overhead. But as I mentioned in my presentation, AV1 also comes with several useful coding tools such as RPR and the screen coding tool. So it's possible that an AV1 encoder can provide benefit while keeping the encoding complexity similar to a 264 encoder. In this case, we can significantly increase AV1 coverage.
Got it. Thank you. This next question is for you as well. Would you consider other codecs such as HEVC and VVC?
Sure. We are always looking for better codec to improve meta user experience. But however, upgrading to a new codec is complicated. There are technical and non-technical challenges, such licensing. I'm not the right person to talk about non-technical issues, so let's focus on technical challenges. And adding a new codec would increase our infrastructure complexity, especially if we only enable the new codec to high-end devices. In this case, we have to maintain different codec in different code conditions. We don't want to have too many codec combinations in our infrastructure. So the benefit of a new codec has to justify the cost dealing with the adding complexity. And here I'm talking about infrastructure maintenance complexity instead of encoding complexity. So in the case of AV1, it provides improved compression efficiency, and more importantly, it comes with RPR and the screen coding tool support. So the benefit of AV1 codec can justify the cost. And For comparison, HEVC and VVC are also good codec options. However, HEVC baseline profile does not support screen content coding tool. VVC baseline profile support IBC, but not a parallel mode. In this case, hardware codec support could be a concern for us.
Got it. Thank you, Yuchen. By the way, we received a comment from Nicole saying that they love the board in the background.
Thank you for noticing.
Okay, on that light note, that marks the end of the first Q&A session. Thank you so much, Nicole, Thomas, Kirk, and Yuchen, for taking the time, doing this presentation, and engaging in the Q&A session. We do have more talks and live panel coming up next, so please stay tuned.
Thank you all, and thank you,
Welcome
Meta.
back from the Q&A session. How fascinating are these technologies that drive the innovation at the core of video at scale? Our next speaker is Michelle Munson, the co-founder and CEO of Eluvio. Michelle is an Emmy Award-winning technologist who previously co-founded Aspera in 2004 and led the company as CEO until May 2017, including through acquisition by IBM in 2014. She co-invented the Aspera fast transport technology used in the digital media supply chain. She will discuss the benefits of the content fabric, an open and decentralized streaming, content distribution, storage network built for the third generation internet. Let's dive in. Over to you, Michelle.
Hello. It is my pleasure today to talk about a new approach to video at scale over the internet. I'm going to be talking about the Content Fabric Protocol, which is a new decentralized and open protocol for video from source to output, built with the concepts of bringing media and metadata and processing all together in one dynamic protocol. The features of that allow for new types of interactive and live content experiences, latencies, and also simplicity. The protocol itself brings together the functions we've traditionally thought of as separated content distribution and media stacks for transcoding and packaging, as well as security into the protocol itself. It's also designed to be tamper-proof and allow for content provenance through the blockchain security model, and really sets it up to be a foundation for the new video economy. So you may be wondering, why did we do this in the first place here at Eluvio? At the top line, we all know that video is most of the internet. It's over 80% of the traffic. It's also $500 billion of value, expected to grow over $1 trillion of value. And yet, even so, the ways that we deal with video over the internet were really designed for data. And arguably, we're still approaching our content in video workflows with files and bytes rather than doing it content natively. We can see the results of that in the complexity that we face. Most modern professional media workflows are really complex, and they are multi-tier. They typically have a number of microservices that are knitted together. And then finally, there are certain constraints about the efficiency, the scalability, and also the latencies that CDNs and media clouds together have sort of forced upon the situation. The Content Fabric Protocol is content native. It's built so that we can not only address content in a way that fits its characteristics, it's also built to allow for all of the functions that we typically think of in multivariate content to actually be part of the content itself. Finally, it's designed to be self-proving, which is very important, we think, in the way that the economics are shaping up. We all know that very little has changed about how we package and deliver content over the last 23 years now. In fact, I think the same workflow has been going since about year 2000. We typically start with source media. We then transcode and package it into several file variants. We usually push those then to origin servers. And finally, we rely on a plethora of CDNs to provide edge caching to improve the performance to the consumer. Of course, this has many challenges, as we all know, the top of which, of course, is internet congestion, the limitations in having to do this over and over again with so many file variants. And then finally, the constraints that multi-tier final to edge architecture forces upon what we can do. And we see this especially when we think about the fact that most content has many different variants of the same thing that are not only published by one company, might be published by many. Think about an international feature film. There might be over 200 different variants by the time you think of the subs and the dubs and the DRM and the packages that we produce along with all the bit rates to the consumer. Also, with cloud-based services, which have obviously become the norm over the last 15 years or so, media, metadata, and processing are not together. And we have to go through many contortions to try to bring them together in our complicated workflows. And then the content economics are really in favor of the distribution platform, not in favor of the content owner or the creator or even the audience. Finally, when we look at an application like content or ad insertion, we can see this all coming together. We have an inherent trade-off between the server side and the client-side implementations. On the server side, it's almost impossible to personalize. It can also be slow and also difficult to get a good experience. If we work on the client side, we might be able to personalize, but we can't scale. And along with that, we can see that most of the stitching architecture really is a profound example of the fact that the media, such as the baseline channel, the metadata that's going into deciding how to stitch, and the actual stitching itself are all separated. If we look at this in the pipeline, we see something like this. We've got our core content coming in, being transcoded and packaged. We have some kind of server-side ad stitcher technology that might even be elsewhere. And then we have the control and the data that's trying to drive this from the ad content standpoint. So this brings me now to the foundations of the content fabric technology, which is really quite different from the approaches of the past. Most importantly, this is built as an internet protocol. It's open. It's open so the protocol nodes can be extended at any time, and all of the nodes run the exact same software, much as we think of BGP routing in the internet. It's application layer and built to be fast so that we're not doing file I/O stop-offs, and so we can have fully pipelined serving from the raw source parts to the output that the consumer is experiencing with 4K live streaming as well as interactive content. It's simple because all the functions are built to tie together in the protocol itself by design as opposed to being workflow-based. And it's built to be efficient so that composable content, multivariant content is built intrinsically rather than being done through the upstream of the workflow. It's secure. The content itself protects itself in a trustless model that combines together the encryption and the DRM and the authorization that also leans on the state of the art in blockchain security, and it's transparent. The transparency allows for engagement to be proven on chain and also the access control in the content to be inherently part of its versioning. And finally, it's just in time and able to self-compose. This allows us to do personalized, stitched, and interactive kinds of experiences that we couldn't do before and makes the lift on that easy for those that develop it. So with that, I'd like to take you into the details of the protocol. We've examined that it's one software stack. It's content addressable. And this is very unique because content objects underpin the way that content is stored and referenced in the network. I'll be showing those in just a minute. All of those content objects allow for self-composition and creating just-in-time output. Blockchain security, authorization, and also version proofs are foundational to how it works, and every operation in the protocol is fully pipelined. At the very top, the content object is the way that all content is referenced and stored. It is a copy on write structure, which means that as new versions of content are created or objects are created, all of the previous version is maintained and only those parts that need to be updated are added or changed. Also, the content object has a cryptographic hash, which becomes its signature. That hash is committed in the blockchain of the protocol, which is the other facet of it, and allows for storing that version as it evolves over time. This object mechanism combines together with the dynamic aspects of the protocol so that when a client comes to the fabric and makes a request for a URL, that URL is literally evaluated on the fly. That process will refer to the lowest layer of the protocol that knows how to locate the base parts of that content object, which can be raw media, metadata, or code, to then bring those over the network to render the code against the media and the metadata and produce the output. And finally, that process is under the control of an interface for access control, also governs the encryption of the parts from the source party to the receiving party, including with strong DRM, through the blockchain contract that's associated with that content object. What's really, I think, remarkable is the fact that every content operation, whether we're producing HLS or Dash streaming video, file downloads, TARs, images, static metadata content for just reading on web pages, you name it, all follows that same process. And all of the source material that comes into the fabric is one of these base content objects with the parts that are built and sharded throughout the nodes in the network. This is governed, of course, by blockchain authorization that is inherent in the content objects. This is really interesting because it means that when this kind of componentized and dynamic output is being accessed, that access goes against a policy that's data in the content object itself and also committed on chain as part of the object's version. That policy can include any business rules. So you can do things like windows on theatrical content for time or geography. You can enforce traditional user and group access control. You can also implement content monetization, where this becomes a way of providing access passes or enforcement of subscriptions. And finally, you can take it all the way to a pure Web3 native approach, where the criteria for getting access is whether the accessing client owns an on-chain blockchain instrument like an NFT. Finally, this all combines together into a global and open network. As I mentioned, the nodes that run the Fabric protocol, because that protocol is standard, nodes can be added at any time, and they all run the same software stack. So any node can provide ingest, any node can provide egress, and all participate in the storage and the serving of the content object parts as part of the dynamic just-in-time rendering protocol. What are the results? Well, you can use this for live streaming, for VOD, you can use it for server-side ad insertion, you can use it for automatic search and clip generation, you can use it for interactive content, and you can also use it for building factories of media tied to on-chain ownership. Now I'm going to show a few demos of this, and I want to just start with an animation that will let you see how this works in practice for publishing VOD content. So in this case, you can see we have a file-based media source. The ingest process within the fabric creates parts that then are assigned to nodes in the network according to the decentralized hashing and partitioning algorithm. Those parts are then fetched on demand as a client makes a request to any node. Those parts go over the network and are processed just in time through a just-in-time transcoding capability that's part of the core Fabric protocol. And then finally, you can see that the technical metadata that's part of the base content object is also accessed as needed to determine things like, for example, what bit rates are being used when that just-in-time happens, just-in-time transcoding happens, what audio tracks are included, etc. Finally, it's important to sort of appreciate the pipeline that's happening here. You can see there are no stop-offs. So instead of making a file version, transcoding, pushing all those variants across, waiting for those file transfers to happen, hoping that you've got stuff cached at the edge, instead that dynamic pipeline supports each client's request wherever it happens in the world and without those stop-offs. And we can take this another step and apply something like forensic watermarking. Notice that nothing changes. The only difference is that now, instead of making a single version of the parts, if we're using, for example, something like the Niagara watermarking technology, there are two versions of the base media parts that are generated. And those two versions become base parts that are requested. And then the just-in-time process can actually utilize things like or be extended with the watermarking algorithm to determine the composition of a sequence. That sequence then being used to generate a unique A-B segment pattern. What's important about this is that any kind of compositional function, not just forensic watermarking, but anything you might want to do in the pipeline can be applied this way and extended without having to build a custom workflow. And I wanted to just do a quick demo here. So we'll play out Warner Brothers Flash, which is utilizing this technology. And a couple of things that are really, I think, fantastic are the Flash here as the feature film is being served directly from the fabric, a single master object, including support for all of the different language dubs, of which there are, roughly 20, 30 provided by Warner Brothers. The transcoding is done just in time. The windowing for access control, because this is a digital OTT film release, is enforced directly in a policy on the content object itself. So we do not have a traditional CDN, we do not have a media cloud, and we do not have external functions driving rights or DRM. All of that is provided for in this one dynamic pipeline with one source object in the content fabric, playout happening globally. And of course, this is interesting because it allows us to also get at per user engagement, session by session, and opens up transparency in terms of knowing what's happening in our pipelines. The live streaming case is similar to VOD, the only difference being that the fabric advertises the core parts ahead of time so that that full pipeline stays consistent and full end to end. And this allows the HLS segments being generated to the player to be delayed literally just the 2-second segment duration plus a few hundred milliseconds of propagation time. End-to-end live streaming latencies of 2 to 3 seconds globally for any client without having to perform contortions in the network or in the protocol. And I'd like to do a quick demo of this as well. I'm just going to pop over here, and you can see this is a live stream of FS1, one of the feeds coming into the fabric being streamed out with HLS. And this is actually using the ultra low latency player profile we've configured on our HLS.js open source player. The end-to-end streaming latencies here are 2 to 3 seconds globally. And notice we're doing this without any custom protocol configurations and with just the responsiveness of the fabric pipeline. Now, finally, we can take a look at this in the context of ad insertion and dynamic content insertion. Same idea applies, but we extend our pipeline now so that we are not just doing live streaming, we are also inserting in that just-in-time pipeline additional content, in this case, ad content. And you can see we can also capitalize on the capability of the content objects to have custom code in their WebAssembly stack that's part of the protocol. That custom code can then read data and also execute so that it provides the insertion functions. Those insertion functions can be any business policy. And then finally, it's also interesting to note that metadata can be added dynamically to the live running streams to trigger those insertions. So you can do it directly from an API or from traditional triggers like SCSI sources. We now have a self-serve architecture for content insertion, ad insertion, which can apply any business logic and bind together the content with the user data without limitation. And finally, I want to provide a quick demo of this, which I'm going to do on the Apple TV. This is a live streaming channel, weather channel coming to the fabric and streaming out on an Apple TV that I've connected directly to this demo. I'm going to trigger an ad insertion through the API. This will be using a selector function, which is actually code in the fabric that will then choose the ad, which is also in the fabric to bind into the channel. It's going to do that based on a simple algorithm in this case that selects a local ad for the region of this content. I just triggered it, and that will come up in roughly 10 seconds. One of the things you can note about this is it's entirely data-driven. So we can make that function, the selector function, as advanced or simple as we like, and with whatever business policies we like. And here you can see we have the Arizona Lottery ad. This will play out, and then we'll be switching back to the main Weather Channel feed. No external software, no custom workflows, just fabric functions. Kevin likes the lottery. And we're back. Hopefully you've enjoyed these demos showing you what you might do with the Content Fabric protocol for your live streaming and your VOD streaming at scale. We look forward to hearing from you. Feel free to connect with us via our website, Twitter or LinkedIn, or contact me directly, michelle.munson@eluv.io. Thank you.
Thank you, Michelle. Managing media at a global scale can be so challenging. Our final presentation is by Ray Zhang, the head of engineering at Heygen. Without revealing much, it is one of the areas of confluence where we see large innovations are being driven at. This is the place where generative AI meets video. I'm so excited to learn more from Ray about this new tech. After Ray's presentation, we will host another live Q&A session with Michelle and Ray. After the Q&A, we will host a live panel discussion where a few thought leaders from the industry will join us to have an open conversation about at-scale systems. Without any delay, let's hand it over to Ray.
Hi everyone, this is Ray, Head of Engineering of Heygen. Today I'm going to talk about one of Heygen's products, real-time avatars. At Heygen, our mission is to revolutionize content creation by replacing traditional cameras. Next, I'm handing over to Joshua, CEO of Heygen, to introduce what Heygen does.
Heygen is an innovative AI-driven platform designed to simplify video creation, delivering results 10 times faster. Choose from over 100 pre-designed avatars or craft your own. Simply provide a script and watch as our AI swiftly produces captivating videos. Boasting over 300 voice options across 40+ languages for accurate lip syncing, it effortlessly bridges the gap with international audiences. There's no need for video editing expertise, making Heygen ideal for marketing, sales, training, and onboarding initiatives. Its enterprise-grade features guarantee smooth collaboration and strict security adherence.
Thanks, Joshua, for introducing Heygen. By the way, this video is AI generated. He's not actually here with me. If you are wondering what problems we're solving at Heygen and what system we have built in order to generate such kind of video content, please follow me during this presentation. Today, I'm going to provide you more context with Heygen first, and next, I'm going deeper into the architecture of the systems we have built, and last, we'll give you an overview of everything we have present today and what we are building for the future. So as you can see, there are a lot of video problems to solve in Heygen. So the first one is avatar videos, as you just see. They can be used for internal training videos and also used for the marketing videos. We can also generate this kind of personalized video messages massively with our APIs. There are some other great features we built. So for example, the video translation. So for example, if you are a YouTuber in English, but you want to reach more audience in other areas, for example, Spanish, also you maybe some reach the audience in the Asian countries, you can simply upload the videos to our platform, and our platform can translate your videos into other language with our Gen AI capabilities. It will provide perfect voice clones and also the lip sync. Last, we provide our real-time avatars capabilities. With this feature, you can build a virtual assistant for your customers to communicate them in real time. So this is a demo video, which is the same video as the previous one, but speak in Japanese. And this is generated by our video translation feature.
AI がビデオを作成します。40以上の言語で300以上の回の
Yeah, but today, what I'm going to cover is our real-time avatar product. So first, what is actually a real-time avatar and what it can be used for? So a real-time avatar is a virtual avatars that you can communicate with in real time. You can ask him or her questions, and you can also use it for the some other use cases. For example, you can use it for as the interactive e-learning, video conference, and also customer support. Next, I'll show you a demo which is built on top of our real-time avatar APIs. Here,
Hello.
I'm communicating
How
with
can I
these
assist you
virtual
today?
avatars. I'm asking her questions, and she can reply to me in real time.
Tokyo is the largest city in Japan.
Cool. Yeah, if you are wondering how we build this system and what challenges we are solving, please follow me to the next section. So next, I'm going to talk about the architecture of the whole systems. So our real-time avatars system is built on top of a WebRTC, which is a real-time P2P communication protocol. There are three main components in our system. The first one is a signal server, which is used as a WebRTC signal channel. And next, we have a WebRTC streaming server, which is the servers connected with client directly to deliver WebRTC streams to the client. And the last, which is the most important component of our system, is the GPU workers, which is to do the AI inference to generate AI avatar videos. So the big challenge of the system is that how can we make the machine learning model inference fast enough to ensure real-time experience? Next, I'm going to talk about some key objects of our system. First one is session. A session is just an abstraction of WebRTC connection. In addition to that, it also provides more information related to our system. For example, the avatars and the voice. So because our system can actually support different types of avatars and voices, you can pass whatever avatars you want to use and whatever voice you want to use if our system support. And also, you can adjust the video quality you want. You can change the video resolution, sort of stuff. For the session, we actually have 5 states. First one is init state. When you want to start sending the real-time task to our system, you have to create a session first. After creating the session will put into an init state. And next, you want to establish the WebRTC connection with our servers. So in this case, you can call the start APIs, and then our servers will try to establish a connection with the client. In this case, it will be in the connecting state. But after the connection is established, it will be put into an active state. After all the tasks are done, the customer can choose to close the session. So he can call the close APIs of our service, and then the session will be put into closing state. During this state, our server will try to clean up the resources. After all the resources are cleaned up, it will put into the closed state. Another key object of our system is task. So a task is just a real-time inference task, usually containing a text the client wants our avatar to say. So currently, we only support text input, but in the future, we might support some other input format. For example, audio. We might also want to support audio streaming and text streaming data. As I said earlier, our system consists of 3 components. The first one is signal server. So in addition to act as a WebRTC signal channel, it also provides some external APIs. So it has 4 APIs here. One is the new API, which is to create a session, a start API,
which is used to tell our server that we want to establish the WebRTC connections. Then our servers can provide the ask offer to the client for the client to answer that offer. Then we provide these stop APIs to stop the session. And last, we provide this sending task APIs, which for the client to send a text to our server to generate the AI avatars. This signal server is also used to manage all the sessions and tasks in our system. It has a global view of how many sessions one server is handling and how many tasks a worker is processing. Next, I'm going to talk about the worker, which is the most important part of our system. So the worker is a component which is to do the machine learning inference to generate AI avatar videos. So usually the task in the worker is executed in steps. The task is divided into 5 steps and executed in a pipeline way. Firstly, it tries to pull the task from the signal server. After getting the task, it converts the text into audio using our text-to-speech capabilities. Then we segment the audio into smaller segments, like 3 or 5 seconds. Then we feed the segments into our machine learning models to generate the avatar videos. After the video segments are generated, they are streamed to the WebRTC streaming servers. And that server is responsible for delivering those videos to the client. All these steps are executing the different steps concurrently, which can provide a better performance. Another optimization we do in this service is that it's called session stickiness. Some background about this is that so because our system can support different avatars, but different avatars actually have different artifacts and different model parameters. So in order to support different types of avatars tasks, we have to swap the model parameters out from the GPU memory and feed in new parameters. But one factor is that the GPU and CPU data transfer is really, really slow, which can become bottleneck of our system. So one optimization we do is that we actually make one session stick to one worker, which means that if a customer is continuous sending the task to our service, that model parameters will always live in the GPU. The next optimization we do is that we actually implement a tiered cache to improve the data transfer performance. As I said earlier, the GPU and the CPU data transfer is very, very slow. So we implemented a 5-tier cache to reduce this overhead. The first tier is the GPU model, which always live in the GPU memory. The next tier is called pinned memory. So pinned memory is a special area in our RAM, which it doesn't swap the data to disk, which makes it much faster than the normal RAM. So next tier is the normal RAM, and then the local disk. And last is the remote cloud storage. In this case, we use S3. Yeah, another optimization we do is called prefetching. So if a customer or if a client calls the start session APIs, it usually means that it definitely will send the tasks after this call. The connection establishment will take some time, right? So at the same time, when the client calls this API, actually what we can do is that we can ask our workers to download the model parameters and artifacts immediately. When the client starts to send that task, the model is already there. So we can minimize the network cost in this case. Next, I'm going to cover the streaming server of our system. So the streaming server is a very simple service. It just used to connecting with the client and keeping the WebRTC connections. It provides one single WebSocket endpoint to receive the video data from the workers. There's no business logic at all. One reason we do this is that if there are a lot of business logic in the service, we probably end up with deploying the service very frequently. But we don't want to do that because it keeps a connection with the client, right? So if we do deploy, we have to handle all this like a reconnecting, which will provide very bad experience to the users. Another benefit of this is that like in the future, we might support other types of workers. If all the workers can just respect the WebRTC endpoint protocol, which it will make the integration really, really easy. For example, in future, we might support like the CPU inference workers and maybe some other types of avatar, for example, photo avatars. Yeah, I have covered everything about our systems. Next, I'm going to talk about like, some other exciting stuff we're building for real-time avatars. First, as I said earlier, we're working on audio streaming and text streaming. So with audio streaming capabilities, the users can use their own text to audio service and streaming those audio data to us. Also, they can probably like just talk through this channel directly and sending their voice directly to our service and let the avatar speak what he speaks. Secondly, we are working on the text streaming. I think one very popular requirement is that like some customers want to integrate our real-time capability with ChatGPT streaming APIs. But ChatGPT streaming APIs very, very slow if it waits for all this text to be generated. So if we can support text streaming, the customer can actually like stream those texts to our APIs. And while the ChatGPT is generating the text, the avatar can speak at the same time. We're also working on improving our inference performance. One thing we're doing is that we are trying to make our machine learning model run on CPU. Although the quality might not be as good as the GPU inference, but it's much more scalable because currently it's really hard to get a large amount of GPUs. But with CPUs, we can scale this capability to more hosts and serve more customers. And lastly, we are working on the SDK because WebRTC is actually a very, very complicated protocol. Some customers like really struggle to use. So if we develop some like SDKs that can help the customer integrate with our AI capability much easier. So if you are interested, we provide our beta testing link here. So these APIs are still in beta. If you want to test, you can simply provide your information in this link, and we can have you join our beta testing. I also linked the API docs for you to integrate with our API easily. In addition to real-time avatars, we are also working on some other great features on top of our avatar capability. First one is called video translation business. We want to bring our video translation to the next level. For example, we are providing the proofread capabilities, which means before generating the video translation videos, you can actually edit the translated text to provide a more accurate result. We also provide 4K output and longer durations. We're also working on the multiple speakers features for the video translation product. So next thing we're working on is called like realistic avatars. So it's a feature for everyone who wants their avatar to generate videos. So the users can just upload a 30-second video clip to our system, and after 5 minutes, you can get a custom avatar used for video creation. Cool. That's all I have covered today. If you have any questions, feel free to reach out to me. Thanks.
Hello again, everyone. Welcome to the second and the last Q&A session for today. We have with us our speakers, Ray and Michelle. Thank you so much, guys, for joining us. Again, a quick note for everybody attending the event. Please do add your questions in the Q&A section in the events page. So without further ado, let's get started with our first question. First question is for you, Michelle. Content security remains paramount in the streaming video. Can you talk about the security benefits of your approach and your recent integrations with Nagra, and your approach to per session end-to-end content security in streaming video?
Great question. Before I answer, I thought I might give a little bit of context because our talks were very short and the content fabric protocol is a pretty big idea. So the context behind this is that I myself and some of the rest of our team worked for many years in the traditional media supply chain of basically making file copies of everything and moving them around and then getting them out to the CDN. And you probably got from the beginning of my talk that was one of the big motivators for thinking about a dynamic, compositional, and decentralized kind of protocol that would replace those workflows. That's really what the content fabric protocol is. And then, of course, it runs across a ever-growing network of nodes, right? Like other internet protocols do. It's application layer. So not trying to change TCP/IP, of course, but build on top of it. So with that kind of a mindset, then there are many parts of what has been done in isolated steps in media workflows that are rather fundamental. And one of those is, of course, content protection, right? And all of us are familiar with the fact that especially high value content has to be secured. There are lots of, I would call it sort of standard or typical ways of doing that, most of which involve trying to secure the environment, right? Because the content itself can't be intrinsically secured as it goes through all the chains of the workflow, especially as it crosses, different vendor environments. So one of the most basic ideas in the Fabric protocols, we're going to change that. We're going to turn it around. We're going to make the content the first-class citizen, and we're going to give it its own self-protection. And we do that through the cryptography of the protocol. And then that cryptography uses a new generation of crypto ideas and also even algorithms that come out of the blockchain world, which include trustless encryption technologies. And by trustless, I mean that the content itself can get encrypted from an owner to another party without having that re-encryption process actually reveal not only keys, but even give any control, if you will, to an intermediary process or to the infrastructure. And why does that matter? It means then the content itself can be self-protecting as it goes from one owner to another, right? Or from an owner to an authorized audience. And so getting back to the original question, so how does the content fabric do that? Well, one basic thing it does is provide for this kind of content owner-driven encryption and proxy re-encryption, which layers on top of that anytime something's served out to a recipient. And then that whole model basically verifies the identity of the participating parties through blockchain identities. And this is important because it gives you a way to make that universal through the whole chain from the source media to the output stream. And then the last point is you can put into the dynamic part of the protocol new features like forensic watermarking. And we recently did that with Nagra, which is one of the leading and sort of Hollywood approved technologies for what's called, AB or consumer scale streaming forensic watermarking. We did that. Here's the big point, right? If you watch the talk, you saw that just-in-time transcoding pipeline that's part of the Fabric protocol. We were able to incorporate the forensic watermarking directly into that as another feature. And then the mark itself is seeded with the unique, if you will, address of the user itself. For example, if that's a wallet address, like a blockchain wallet address, you end up with a unique seed combined with the algorithm itself. And together you end up with a AB segment pattern, which is generated by that just-in-time pipeline with the same scalability as the rest of what we do. So you keep the same efficiencies, you get the personalized mark, and you have it in a way that's really deterministically tied to the user session. And this kind of thing doesn't happen in the traditional, publish from the cloud to the CDN and then go to the consumer. There's many steps along that way, and it's very difficult today to be able to, shut down the leaking sessions, if you will. Whereas in this model, it's very direct, it's very deterministic. And then finally, you can shut down an individual session just by updating the policy for authorization that's held in the content object. So you have an instant off, right? That's one of the, I think, good examples of how a protocol like this changes what you can do, right?
Got it. Makes sense. Thanks, Michelle.
You
This
bet.
next question is for you, Ray. Is there any active work going on to improve the inference performance?
Yeah, great question. So yeah, we are doing a lot of work to improve the overall performance of the real-time system, not only inference but the overall end-to-end latency. Yeah, so I will like divide them into maybe three categories. One is the model side. We're doing something on to improve the model performance. I think one thing is that we are training a model dedicated for the real-time case. It's a smaller model. We trade off some maybe some quality with the performance, but like for real-time case, it should be like good enough. Yeah. Second thing we are doing is we are improve the model architecture. So currently as I just presented in the talk, right? So our whole inference architecture is based on a pipeline style, but in some parts of our system is still not very pipeline, because for the lip sync model, it actually requires some context. So if we don't have enough context, the lip sync won't be looking good. So it has to wait for some data before it do the next inference. So yeah, so what we're doing is that we're trying to improve the model architectures and making it to be more like a streaming way. For example, maybe in the future, we don't need to augment the audio anymore. We just while we're streaming the audio, we just pass the audio stream to the model, and the model will produce the video stream in a streaming way. Yeah. A third part I would say is the whole architecture and the whole engineering work. For example, some native machine learning operators, they are probably not implemented in a good in a very optimal way, at least in our case. So we're trying to re-implement some machine learning operators ourselves, and maybe try to combine some of the machine operators into one to reduce the context switch, because GPU context switch is kind of expensive. So so in summary, we're doing a lot of work to improve the end-to-end performance of our system. Yeah.
That's really cool. So quick follow-up to that is, what is the current end-to-end perceived latency for the real-time avatar?
Yeah, in most cases, it's 2 to 3 seconds. But I think it's good enough for most cases. But still not good enough for very real-time cases. So I think our end goal is to reduce that latency to under 1 second. Yeah, and also when there are a lot of users using our system, that latency might be larger than 2 to 3 seconds. We're also trying to improve that as well. Yeah.
That's really interesting. Thanks. This question is for you, Michelle. With today's traditional media workflows, there are known scalability limits to delivering personalized content or video. Can you talk about the dynamics a bit more and how Eluvio's approach is aimed to help address that?
Oh, yeah, for sure. So kind of referring back to my talk, the section on dynamic advertising, right? I'm going to use that as my example because personalization, right, is a broader context of the same idea. I think most people are familiar with the fact that the interstitial composition of content streams today is done in I would say a rather legacy manner that has stayed mostly the same, at least for 10 years or so since cloud media workflows got going. And the gist of it, of course, is that you have some kind of server-side stitcher driven by some kind of selecting algorithm that then the streaming pipeline hands off to pass what is otherwise packaged and transcoded content to the stitcher to then respond back with the stitched in stream, right? Problems with that, of course, are that if you're going to scale it, you can't do variants, unique content for each recipient. And vice versa, if you try to do something that's really personal, you can do it player side, right, or client side along the way, but you give up the mass scale. And a perfect example of that is Google AdWords, right? We all get that. There's a little bigger problem beyond the technology, which is it has grossly consolidated the stitching space to a few big players, right? Most of the digital ads are, really dictated by the big ad inserters, right? So the fabric being very different in terms of compositionality frees you up from that problem. And the best way to understand it is to look at that visual pipeline in my talk, where you see that, the protocol is able, firstly, because of the content object structure, it's just fetching over the network what we call the base content parts. Those parts are one bit rate in video terms, plus the metadata parts and the code parts. It's just getting those, and it's never getting anything else. So you save, the time, the storage, et cetera, in doing that. And then those are operated on in that pipeline way to transcode and produce the 2-second segment outputs in terms of streaming video. When you stitch in content in there, because the fabric uses its own model, right? First of all, dynamic code. Secondly, the ability to retrieve parts that are content themselves and can be dynamically transcoded. It turns out that you can transcode unique content into each one of those outputs without losing those efficiencies, right? And that's the key thing. It's like you got yourself a real-time program that allows you to retrieve in the content and just in time transcode it into the stream and finally serve it out to the serving viewer. And so the scalability footprint on that is very close to as good as serving everybody the same set of content or ABR ladder. That changes things for content stitching. It makes it possible to do not just personalized ads, but to really even have personalized channels, for example. And today, one of the big applications of that, of course, in free and ad-supported channels is just that, being able to have really boutique content. And you saw the example in my talk with the weather case, for example.
Right. Thank you so much, Michelle. That makes sense. This next question is for you, Ray. How do you make sure that Heygen's AI capability is not abused?
Yeah, that's a very, very, very good question. Yeah, because as you can see, like the avatar technology is very great, but also it's very risky. It can be used in some very bad purpose as well. But we definitely don't want our avatars be used in those areas, right? So I think we are trying to do a lot of stuff to prevent this. And first thing is like we dedicated document this in our policy and terms of service, saying that like some use cases are not permitted. For example, porn, like particular use case, drugs, yeah, sort of stuff. Yeah. And second, we are doing some automatic content moderations and also manual content moderations on our side. So if a user tries to abuse our system, for example, like he tries to maybe download a video from others and create avatar using that video, that can be detected by our systems. We have a lot of detections. So those the areas I just mentioned in the policy that we can auto detect those, and also for celebrity, we also detect those. And in order to create avatar, we do require that person to give us a video consent, to say that like they allow us to use their avatars to create use their video footage to create avatars. And we also have some detection on that to detect is it the constant video and the video footage used to create avatar are the same person, and they are actually speaking the statement I just mentioned. So and also like they sometimes they can try to fool us by just like replace the audio of the video. We can also detect those because we are doing lip sync. We can detect if the audio actually match their lips. Yeah, but like all the other like automatic detection, right? Those you cannot catch all the like use case all the like cases. So that's why we also have a manual moderation. So we have a moderation team behind the scene to try to look at the content because our detection will have a different state. One is definitely reject. Some are like suspicious. The moderation team needs to involve. So they will look at all those avatar videos and try to see if those are valid or not, and make decision. Yes. Yeah. Hope that will answer your question. Thanks.
Yes, that is completely rounded. Thank you, Ray. This next question is for you, Michelle. And it's a bit long question, so please.
Okay.
Just-in-time delivery and transcoding makes sense. But to avoid the compute costs of popular content, we will have to cache and store the transcoded data, right? Is this something that we will have to do as part of the pipeline or use CDN? And a small follow-up to that is, doesn't this cause the same file variant increase that you have talked about in your video?
Let me take the end of the question first. The short answer is no. But the real question is why? Why is this different than just the regular caching of all the things that everyone, basically caching everything that anyone's going to consume, right? The most important facet of the fabric that a lot. Did my bandwidth go? Well, there we go. Can you hear me clearly?
Yes, we can.
Oh, okay, perfect. Let me start over my answer to that. Sorry, I had a little internet glitch there. So, into the question first. Why is this different in the end than just caching all the variants that everyone's going to consume, right? The most important thing about the Fabric protocol is, first I want to talk about the network consumption. If you think about the way we compose these variants today, we make everything that we think someone's going to consume and we push it on out to the edge, right? The question was about the storage, but the first order thing to like absorb in all this is that the fact that we do that means we spend the compute and we spend the network bandwidth in order to do that. And we do it with absolutely everything, right? That's not also to mention the ancillary services that you put around that in order to get all of that pre-made. And so the most important contribution, right, in terms of the resource footprint here is that nothing is ever made, right, and in turns cached, including transmitted over the network, composed into all of its various variants, whether they are bit rates or packaging standards, for example, or audio deb combinations, language combinations, thinking through in the case of interactive apps, views, for example. None of those are ever done unless they're actually used by somebody, right? And then to your second point about the actual storage, right? Once somebody's consumed that, yes, the Fabric protocol caches what it's made. So yes, we do store that. But there's a really big difference from today's edge caches, which is that what we typically think about the necessary locality is very different. For example, Fabric nodes can basically cache on behalf of each other. And because the protocol is so responsive, and this is something that a lot of video people don't believe till they see it, but because it's so responsive, you also don't have to be as close to the end user in order to get high throughputs. For example, with HLS, we do 2 to 3 second, which some people call ultra low latency delivery with standard HLS off the fabric in live streaming. We don't have to, change the protocol in order to do that. That is using fragmented MP4 2-second segments, but people that are deeper into video transcoding and packaging know that most of the attempts to hit that in HTTP adaptive bitrate streaming are, making some pretty brute force changes to the HLS, the way the HLS protocol is done, and having other compromises in terms of the players. And the reason we hit those numbers is because the Fabric's pipeline is very responsive due to, how it's built. And therefore the clients get higher throughputs, the ABR ladders stay higher, and you don't have to be as close. So all of this ties back to your original question of, well, what really happens? Well, you save a ton of network bandwidth, you save a ton of compute doing this and all the ancillary stuff. And then finally, what you do cache, right, really doesn't have to be as local. Plus, you've got this ability to multi-purpose the caching from a set of peers. So I think these are all important to kind of come together to answer your question.
Yes, that does. Thank you so much, Michelle.
You're welcome.
We'll take one final question, and this is for Ray. What is the pricing model for real-time avatar?
Yeah, good question. So for the pricing model for the short answer is that we haven't finalized our pricing model yet, but we have some a rough ideas. Yeah. First thing is there could be different use cases for the real-time avatars. One is that maybe it will be just used for broadcasting, and the users will just use one session and broadcast to many users. But that session will be running maybe 24 hours, 7 days. Yeah. So for those one, I think we have we have some a pricing model like maybe we can provide some monthly subscription for those models, so they don't need to worry about they are broadcasting for too long. Yeah. A second use case that we imagine is maybe some virtual assistant. They will provide this a virtual assistant to many users, maybe thousands or even tens of thousands of users. But usually those sessions are pretty short. They just ask some question and answer them. That's it. Yeah, for those use cases, I think pay as you go is better for them, because usually the sessions are pretty short. If we do a subscription, it will be super expensive for them. Yeah. That's it. Thanks.
Makes sense. Thanks for answering. Okay, so that was the final question for this Q&A session. Thank you once again, Ray and Michelle, for joining us, taking the time and engaging us in this Q&A session. This was very informative. Okay, we now have a live panel coming up next, so please stay tuned. Thank you.
Very cool. Thank you. Welcome to the last session of the day and of the 2 days. We're going to take into the challenges and trends in video at scale. And we're joined by some awesome people from across the industry to go through a few really interesting topics over the next 40 minutes or so. So I'm going to start with some intros. Hi, my name is Tim. I'm an AM here at Meta, and I want to hand over to Tamar. Can you give us your name, your company, and what got your company, what got you here today? And then we'll move on.
Well, hi, everyone. I'm really happy to be here with this esteemed team of panelists, wrapping up what appears to me to have been a very strong video at scale event. My name is Tamar. I'm an electrical engineer by training and have spent over 20 years in the field of algorithms for video processing, compression, and video quality. My story is tightly coupled with the story of Beamr, where I'm the CDO. And having been on board since inception, I've had the pleasure to be part of our exciting journey. We build perceptually driven video encoding and optimization solutions. The optimization process uses our Emmy Award winning quality measure, so cool, and it reduces bitrate creating perceptually identical, fully standard compliant video bit streams. We're also grateful to have an amazing partnership with NVIDIA and are currently working on the launch of an NVIDIA-powered video optimization SaaS product. I'll also add that I'm located in Israel. I'm a mother of 3, and being an Australian-born religious Jewish woman, I try to be a voice for diversity in the tech world.
Really cool. Thank you, Tamar. It's awesome to hear. A lovely introduction. Roberto, I'd love you to answer the same questions. Give us your name, the company, and what got you here today.
So, hey, I'm Roberto Peon, and I am from Meta. And my journey here started with autonomous flying model helicopters. It was an interesting project, and part of what we needed to do there was to perceive the world around us. It turns out that requires video. And it also turns out that that problem was close to intractable. So instead of doing more flying autonomous helicopter things, I ended up doing special effects stuff. And from there, I went to doing augmented reality for live sports TV. And so as far as I know, that stuff is still happening, which is kind of fun to see. From there, I took a sharp left into networking and distributed systems and network protocols and standards. That was fun for a while. I did some things that people probably are still using. And then I went back into video because video is really a bunch of really hard computer science problems, and I love the hard problems. It really makes me tick. I kept doing that when I joined Meta, and did that for a good long time. And now I'm also looking into VR and AR, which of course is a combination of the generation and the recording and display of the pixels. Really cool. Thank you, Roberto. Exciting. I thought you came in via an autonomous robot, so I was excited by that. But I'm going to hand it over to James. I'd love to hear name, company, and the journey that got you here today.
Absolutely. Yeah. My name is James Broberg. I'm founder and CEO of StreamShark. It's always hard to summarize the journey, but I guess I started in academia as a bit of an accidental academic, working in distributed systems and load balancing algorithms, but sort of moved on to the commercial world and started off in the CDN space in sort of fairly novel at the time, multi-CDN optimization strategies. And then, I guess rode the tide of video from sort of 2014, 2015. And now at StreamShark, we're just laser focused on, true end-to-end workflows. We just like to solve customers' hard problems, basically. So everything from signal acquisition or content acquisition all the way through to play out and everything in between. We're focused on making, closed loop systems that, we hope make our customers' jobs a lot easier and de-stresses the challenges that are just growing in terms of delivering really rich content to increasingly complex and powerful end user devices. Really cool. Thank you, James. And to finish, our panelists, Haisha, I'd love to hear an intro from you and the journey that brought you here.
Hi, everyone. Really glad to join this. My name is Haisha. I am a software engineer at Meta in the Instagram media platform team for the last 5.5 years. My story probably started around 18 years ago. I had joined the workforce in Silicon Valley as a software engineer. The first job is actually at NVIDIA, and I was having an interest in video to start with. And my first job spent about 7 years on various playback, video decoding, and firmware driver solutions. And after that, I also worked at Google and Apple on various projects related to video encoder. What really got me here in Instagram and so excited about is the scale and the fact that we're serving billions of active users. And along with it, like the huge challenges that before that I was not that familiar with. So I feel like this is a completely new horizon and super, super interesting work.
Really cool. Thank you, Haisha. I'm really excited by the breadth and the depth of our panelists here today. It's awesome to have so much knowledge in this room. I'm going to dive into our first topic. And I want to ask, when we think about maintaining consistent quality of experience, it's always like a key component of delivering live and on-demand video at scale. And the users of these services are becoming more and more demanding in terms of expectations around lower latency, in terms of rich content and quality and of immersive content and the experience. What tactics and trends do you see from an observability and optimization perspective to address these challenges? Haisha, I'd love to come to you first on this topic.
Yeah, on this topic, I will probably start from the approach of where everything starts, which is the video ingestion. So even though I think quality of experience, people usually talk about consumption, what actually goes into the video pipeline really plays a huge role in terms of the visual quality, in terms of reliability, in terms of like error detection, a lot of the things of the homework that we do when the video was first ingested. And I believe that this is super important. And I think one of the trends that I see is that we're doing more and more of the pre-processing in terms of detection, in terms of like trying to optimize the encoding recipe based on the type of content we receive. And this has like a huge impact downstream in how much of a visual quality and quality of experience we can deliver. Yeah, I would.
Really cool. Yeah, I totally agree with that method of the beginning, garbage in, garbage out. So like if you can put the best quality thing in, the output's going to be so much better. Roberto, I want to come to you next to talk about your thoughts on this topic.
Sure. So I would love to replay Haisha's topic and play at the beginning here, because it all starts at the beginning, as he pointed out. And at the start of the stack, we have better sensors these days. The cameras are up just so much better. You have in your hand what you would have paid hundreds of thousands of dollars for not that many years ago. And it has driven a lot of change everywhere. So it's driven us to better codecs because we just have a very wide need. You can't spend your way out of this problem like you could when we only had a few cameras that were really nice. And then now we need better protocols because there's more people slinging more bits for more pixels around, and they have more of an expectation of interactivity than they did before. And that's a really fun, hard challenge. And that leads us also to the fact that we need better algorithms for choosing how to manage what bits and what quality to send, and figure out what the network is doing that might make it hard to do that kind of thing. So I think it's also really interesting that the difference between live and not live is also getting smaller. And I think what we're seeing is that folks are playing around with what that means. And so the differences exist in the architecture of various parts of the stack, but the quality of experience is really the differentiating factor between a lot of different product stuff right now.
Yeah, really cool. And even this conference is a good example where we're blending live and pre-recorded content in a very dynamic way. And it's really exciting to see that. Tamara, how do you see these challenges in your universe?
So I would probably focus on the quality of the video as an important factor in the quality of experience. And we've seen a huge leap in the awareness of the industry for actually the importance of incorporating perceptually aligned quality measurements into the loop. And I think actually the talk given yesterday by Meta's Denise Noyes is an excellent case in point of how we're moving towards finding better quality measures to do the work and have them in the loop to get an overall better quality of experience. Years ago, when Beamr started with quality-driven encoding, the discussion was generally, why would you want to do that? And companies that did something related to quality at the best case used PSNR. And we've definitely over the last decade, guilty as charged. Over the last decade, we've seen an evolution, in large part thanks to VMAF, donated by Netflix. And nowadays, nobody asks, why do you care about the perceptual quality and why would you want to measure it? It's how do we do it and how do we do a good job of it and how do we really make sure that it's perceptually aligned. Now, of course, it's always a balance, right? And if you reduce bit rate and maintain perceptual quality, where do you get the extra compression efficiency from? And I'm sure we'll touch on future codecs as we move on in this discussion. But to me, bottom line, it's about getting better compression efficiency, using everything at our disposal while keeping our eye on the ball for the visual quality. That's fun.
It's the big one.
And making sure that we are using the best approaches and using all the tools we have to measure the quality in the loop. And that will yield the better quality of experience. Again, it's one factor. It just happens to be one that's particularly close to my heart.
Yeah, in-loop quality measurement is a really exciting development. I had off camera, I had an exciting reaction when you said PSNR, because my doctorate, I use PSNR as my quality measure because VMF didn't exist yet. But that's why I was like, oh no, on that side.
It used to be that every paper we read that started with, PSNR is a terrible metric, but we're going to do everything with PSNR. Yeah. I was like, forget it.
guilty on that side. That's so cool. James, I would love to come back to you to close this topic for us and look at the end-to-end. I hand it to you.
Yeah, absolutely. I guess, given my background and my company's background, particularly, originating in the CDN space, we're quite focused on deliverability and observability. And I think the advances that have occurred in that space in the last 2 to 3 years have been pretty phenomenal in terms of just understanding more about the actual client-side experience. And I guess, moving to a standards-based approach to do that, that's kind of, compatible across vendors as well, is a huge advancement. So, CMCD has been, massive for us, and I think for many of our peers in the industry, in terms of actually having real data to understand the client-side experience. And it's not to say that it didn't exist 3 or 4 years ago. There was RUM, there was other techniques, but the techniques were pretty disparate in terms of how they operated, or they were vendor-specific. And quite often back then, 3, 4, 5 years ago, you'd run a large event, and if they weren't using your end-to-end stack, they'd say, how did it go? And you go, well, it came off the CDNs clean, it came off the mid-tier cache clean. As best we can tell, it's gone well, but we didn't have that kind of uniform client-side insights to really understand how it's gone. So, I think it's just a phenomenal kind of advancement for the space. And I think it ties back to pretty much what all the panelists have spoken about, because you can use that information to make decisions on contribution. You can use that information to make real-time decisions on which bit rate lanes you might want to include or drop for a high-profile, high-scale event. So, it's I think that's really brought it all together, and it can really inform all the decisions that we make from contribution to transcode and play out.
That's really exciting. Actually, I'm going to throw in an unprompted question and ask, what do you see the development next in our observability? So the CMCD is going now, like how is that evolving for the next?
I think it's just kind of echoing what I've said. I think making real-time or near real-time decisions based on what the client experience is, I think is going to be important. Like if you're spending all this energy making 6 bit rate lanes and only 3 of them are being used, you can make a decision to conserve resources. And we're all talking about the greening of streaming these days. So if we're consuming less data center resources, we're emitting less CO2. I think that's a net positive, and controlling bandwidth that's going out on the wire as well. So I think that's just a example, but I think it's got applicability to make better decisions down the pipe for live and on-demand context.
That's really cool. Thank you, James. I'm going to move to our next topic and ask, and switch gears a little bit, and look back and say, over the last 20 years or so, we've seen the rise of generic IT hardware. We talked just about data center efficiency. Before, there were no data centers doing processing video. It was all custom hardware in racks, in broadcast units. And we've seen this rise for media processing and consumption, both because the client devices and the phones have gotten much more sophisticated, so they can do more processing as well, both for transmission and receiving, and TVs, etc. We're seeing the rise now of custom hardware as part of that flow, to accelerate processing and to make playback more efficient, to drain the battery less. Like, what trade-offs do you see when we're investing in the power efficiency of custom hardware? How is that being traded off with other advancements that we'd love to see? Tamara, I'd love to come to you first here and let you noodle on this question.
So it's a great question. And being a dinosaur, I do remember the days where encoding a video was black boxes, DSPs, ASICs inside. And over the years, as CPU power grew and Moore's law was, in its element, software encoding became much, much more popular and, across the board. But I look at the video today and there are so many challenges across so many dimensions because there's an explosion. There are cameras everywhere. All of us are walking around with, this 4K or at least full HD, often HDR, 10-bit, 60, 120 frames per second, creating this video. And there are a lot of more complex workflows, low latency, whether it's a few 100 milliseconds for live streaming or even a dozen milliseconds for immersive video. So we've got that making things more complicated. Then for a long time, H.264 AVC was, pretty dominant on the scene. Finally, we're starting to see adoption of better compression efficiency, more sophisticated codecs, and that adds more complexity and processing demands to the process. So when you put everything together and add to the fact that the CPU isn't growing and increasing in power in the rates that it was predicted by Moore's law, because we're kind of reaching a saturation point. Putting all that together, basically, I think the switch to hardware for encoding at scale is inevitable. Now, obviously, hardware encoding has a significant benefit of reduced power, low latency, cutting back costs, but it comes at a price. It comes at a price of lower flexibility of the encoder. And you have the limitations of whatever hardware encoder you have. And generally, if you're not Meta or Google or some other empire, you can't really build your own platform, and you have to make do with the hardware encoders that are on the market. So we've actually, as I mentioned, been fortunate to partner with NVIDIA and create a hybrid solution where we use the NVIDIA NVENC hardware encoder underneath, and we've ported our content adaptive technology to the GPU to run very closely with the hardware encoder. And this essentially gives a hybrid solution that can enjoy the benefits of both worlds. So we've seen that, we can cut costs by a factor of 10 compared to a software solution that was, of course, also heavily optimized just by using this underlying hardware encoder and a GPU kind of optimization over it. And a huge advantage is that it means that in the workflows that have GPU processing, the encoding is already done on that GPU and the raw data is there. So I think that's a good point to hand over to James, because I know he has something to say on that point.
Yeah, absolutely. I think we've really ridden the wave as well in terms of leveraging, what started off as sort of consumer hardware from NVIDIA. Like, yeah, we've had less to do with sort of ASIC type stuff and more to do with sort of leveraging, this evolution of NVIDIA GPUs that perhaps was driven by gaming and, life sciences and machine learning, but ultimately has turned out to be quite effective for media processing. So yeah, it was, I think until quite recently, it was quite a trade-off between video fidelity and achieving cost-effective scale. So we certainly got in early. It got us that scale, but I think the quality was lacking for the more discerning customer that's super concerned about video quality. But ultimately, there's been a bit of a commodification of live streaming, and it's kind of helped meet the aims of providing cost-effective solutions for customers. So, we were sort of in early at the, Kepler or Pascal stage in terms of leveraging it in our stack. It's only quite recently with, the 2080 RTX or the T4 in the data center that it got to the level of fidelity that we thought was good enough to roll out to, more sophisticated use cases where there's more fidelity required, whether it's AR or VR or, 1080 60 frame sports content. Like it was getting finally to the point where it was comparable to the gold standard X264 type processing. So that was a really exciting step for us, and that's let us kind of baseline on that as one of our dominant platforms. And then it's continuing to evolve now. All this great codec work that's happening, for instance, in the AV space is going to get unlocked by the latest generation, where we finally do have AV1 GPU accelerated encoding, where it was just as great as it was, not practical again, unless you're at a meta scale, for us to kind of bring that into our pipeline and actually offer timely AV1 type encoding, and to reap the benefits of that approach. So yeah, we'll continue to watch the space, but it's been a game changer for us.
Pretty cool. Thank you, James and Tamar, for taking us through your experiences. Haisha, I'd love to come to you to talk about Meta's experiences adopting hardware and the trade-offs that we've had to make as a company.
Yeah, so interestingly, even though I want to talk more about experiences Meta, which is more of a custom ASIC-based hardware encoding accelerator, I find that the observations are largely similar. At the beginning, the power efficiency and compute is such an important factor to consider. But the fact is that the hardware encoder is just perceived to be inferior compared to the software encoder's compression efficiency and quality and fidelity. And that was like what is holding it back on a large-scale adoption. There's too much trade-off to be made, and then people are hesitant to onboard the production encoding pipeline onto this. And there was this magical threshold moment where the new generation of the ASIC suddenly becomes good enough, and then it becomes like really compelling for all the teams to onboard to this system. And I think that the similar thing will also happen if, for example, the next generation or something that gives a good enough experience for advanced codec like AV1, that would probably be the moment where we are starting to see the shift of the workload onto ASIC as well. I'm probably gonna give back to Robert also on this.
Yeah, so as we've already established, I like to go back to the beginning, so I'm going to continue doing that. And the beginning of my journey with video stuff, we had kind of bigger, different challenges than what we have right now. So storage, in particular, was an interesting problem. This was the days of tape, and it started off as analog, and eventually we got digital, but it was still a problem. Like, how did you do the things that you were going to do? The computers didn't have the bandwidth internally, like the bus itself didn't have the bandwidth to do multiple videos. So we started kind of with storage as the bottleneck, and then we got to like bandwidth within the computer itself was the bottleneck. And so that was generally solved at the time by custom stuff. And one of the big players in the industry back when was SGI, who no longer exist. And they got replaced with more generic PCs as Moore's law really started kicking butt. And at that time, we saw also kind of the advent of GPUs come in. And we could solve some of the video problems with the limited programmability that we had on these newfangled, supposedly for gaming devices. And so we've come to learn they definitely have more use cases than just gaming these days. And then we started to see that the problem changed. It was the same problem in a sense, but the scale went bigger. So now we were looking at, instead of just doing like video that was broadcast to everybody in exactly the same bits, now we're doing it over a network where people have different varying requirements. And so now what we need to do is make multiple streams of encoding so that people can tractably pick the one that actually matches best. And then, of course, that started the storage problem again, became interesting, as James brought up before with the CDN. And of course, these two are very interlinked in fun ways. And so we've seen this cycle start up again. And that's true on the storage side and is true on the processing side. So right now what we have is ASICs that are not obviously user reprogrammable. And it's really interesting that we're seeing, hopefully, some more motion towards being able to do with video codecs what we've seen being done with graphics stuff. So programmable things of, not infinite function, but more than purely fixed function that really makes for innovation in the space. And I'm really excited to see where we end up going in the cycle again. So we've made custom silicon. We are doing that across the industry to make things cheap enough. But now we're maybe thinking about making it somewhat programmable, or I hope we are, so that we can get some of that innovation back. So that's kind of what I'm excited about, is that, it seems like we keep going through these cycles. We're going through another cycle right now. And right now it's specific hardware in the ascendance. And then I think we're going to add the programmability back. Really cool.
Heysha, I'm going to come back to you actually for an unprompted question, because as you were speaking, I thought back to Tamar's response earlier about quality in the loop was game changer for end user experience. How should we think about quality in the loop when it comes to selecting hardware in terms of hardware encoders on that side? I'd love just to hear like 30 seconds on how you think about quality measurement when it comes to migrating from software to hardware.
Yeah, I think the general rule of thumb that I think about it is that we try to benchmark the hardware encoders compression efficiency in terms of like an objective metrics like a BD rate based on SSIM or VMAF, and really trying to see how well it can produce the encodings at a certain bit rate at a certain quality bar. Because I think at the end of the day, that is what really makes a huge, it's a factor in the decision-making process for team to think, is this like a huge trade-off, or is this something that is so compelling that we should just have no-brainer to adopt it?
Yeah, that makes tons of sense. Thank you, Heysha. I'm going to move on to our next topic. We have seen like this huge change in video processing workflows over the years, a very significant increase in complexity from content creation through to processing and coding, where we've been integrating more and more tools, be it ML tools or AR tools. I'd love to hear from each of the panelists, like what are some of the challenges that come with this increasing complexity, and how are you starting to think about addressing them in your workflows and in your systems? I'd love to take it to James first to hear your thoughts on this topic.
Yeah, absolutely. I think to some of the earlier points that have been made, like, yeah, there are less trade-offs now that we're beholden to. So I think, if we can move to more efficient encoding codecs, AV1 just as an example, there'll always be new codecs coming down the pipe. At scale, if you can get a 20 to 30% decrease in content stored and content transferred at essentially the same fidelity level, at petabyte scale and beyond, that's massive. So that's it's cost savings, it's efficiency savings, it's energy savings. So I think it's really compelling for everyone in the space to move to those more efficient codecs. And I think the content itself, as some of us have touched on, it's becoming richer and richer. We're being pushed to deal with 2K, 4K, 6K, 72 FPS, 90 FPS content for immersive applications. So you can imagine just the content size is just ballooning as well. So how we did things 3-4 years ago is not really going to cut it for those types of applications. So that's obviously a big driver to have workflows that can deal with that level of complexity and richness of content. And I'll just touch on quickly, we deal with quite a diverse range of content, whether it's for internal, applications that are quite sensitive, all the way through to external broadcast type applications. But even in the internal space, like with the sensitive content we deal with, like there's a lot of AI and ML applications at the moment around data privacy in terms of redacting sensitive information or faces or things like that that we're working on. My colleagues are working on training models to better handle those types of situations, to deal with complex regulatory requirements around storing private information. So that's a bit of a niche perhaps application of AI and ML, but that's just an example of I guess what's going on in the space.
And to see that coming off client and into the server side, so we start to see this amalgamation of things living in the middle and less happening on the production side and less happening on the client side. It's really interesting. I'd love to hand the topic to Haisha next, and how Meta, what your experience at IG has been for this ever-growing complexity, and how you're thinking about what's coming next. Okay.
Hello.
Cool. I'm going to go on to Roberto because we're having some tech difficulties just at this moment. Roberto, do you want to take the question next?
Sure. So my observation is that the whole pipeline is utterly different right now than it was even like 4 years ago, which for anybody in the tech industry is kind of like, well, yeah, of course, but that hasn't historically been true for video. Things have not changed that fast in this area, but recently they have. And so, the first thing that I think is quite different is that everything tends to start with a mobile device. It's your camera, it's your friend, it's your storage, and you also make yourself look better, or maybe somebody else look better, and you put little sparkles and stuff with filters and such on these, and that's kind of the first part of production that many folk are going to see. And so we're seeing basically a whole lot of client-side processing or client-side pre-processing that makes life interesting for everybody. Some of the quality things that we were talking about before actually get a little confounded by some of these things. When do you reprocess? Are we putting text on it? Like, video doesn't normally have a lot of crisp, clear, supposed to read it nicely text on it. If we're putting those things on filters and then we're uploading them, we're doing something again to it, re-encoding them. Like, how do you deal with that? These are all fun new problems because so much of video production is newly on these client devices. And then, of course, we bring up the connectivity issues. When we were doing things on big, beefy, PCs or cloud servers, those things were fairly well connected. We didn't have to deal with hiccups as much in the connectivity, both, whether it was connected, period, or not, or also like, did the latency change because we went from the West Coast to the East Coast or across a different continent? Like, those things are way more common now, and we have to deal with those. And then the user experience itself is diverse and different depending on what phone and what app and all of these things. So we've had kind of a lot more variation crop up as people are using the devices to do it that way. And of course, none of that is really talking about the fact that we've also seen sea changes in the cloud side. It's just that the changes on the client side, to me, are really amazingly huge.
It's really cool. Yeah, I see those too, and I see our complexity growing as a client surface. Tamar, I'd love to take the topic to you.
So I obviously agree with everything that's been said, and I want to touch maybe on a slightly different angle. I agree with what James said about, needing the better codecs because the complexity of the workflow is growing. But I think we're seeing another interesting thing, and Roberto touched on it. We're seeing companies and the kind of researchers that never really dealt with video, so machine learning experts and analysis and all sorts of AI experts creating videos, analyzing videos. And the video is getting even more and more valuable, right? Because we're doing all sorts of things with it. But these are companies that don't necessarily have in-house video encoding expertise. And on the other hand, they're dealing with this mass of video content, which, the huge storage, huge bandwidth bottlenecks to pass things around. If you want to do training on video, well, good luck with that. And I think this is something that we're actually tackling at Beamr, is we call it democratizing the access to sophisticated video encoders by being able to take an underlying hardware solution that is cheap and wrapping it in a technology that kind of makes it accessible. And you can do something we call codec modernization, which is just take your video. You don't have to be a video expert. You don't have to know the FFmpeg parameters. You don't have to read the manual. And, we'll just preserve the perceptual quality and get a better compression efficiency, reduce the bit rate. And I think so. I really think that's one of the interesting things. If we were always kind of a closed world of video compressionists and geeks that knew the bits and bytes and the standards, a lot of people need access to good video compression, and we really see it as one of our goals to sort of open this up.
Really cool. As you were speaking, I was thinking about our next year's panel. We should talk about storage. Like, all the value of video is growing. How do we start to unlock that value even more? It's a really interesting topic area. Haisha, I'd love to finish this topic with you and give you the microphone for a little bit.
Yeah, so in terms of complexity in video processing, I think one of the angles that I want to talk about is high dynamic range, or HDR video, because a lot of the things that we talked about higher and higher resolution and frame rate, but HDR just throws in a completely new dimension to it. And this is something that is very hard to do end to end, because you have to have an unbroken chain of custody of the correct color space all the way to consumption. So I think, and this goes beyond just video compression. It also has to do with how you do video processing, rendering, mixing, all the effects in AR correctly in HDR. I certainly find this has been one of the most challenging things at IG for the past couple of years. And I think this will continue to be an unsolved problem in the future, with all the things like how do you mix HDR and SDR content, effects that used to be programmed only in 8-bit. Now you have to support this, and including the correct handling of brightness and things like that at the playback side. So I think, yeah, that's definitely something new in the last few years, but it will continue to be a big problem.
Yeah, it kind of makes me curious about, we talk about ML effects and Gen AI, like, are we expecting Gen AI HDR output, and then how we process that as we see that going in the chain? It's a really interesting topic area. I'm conscious of time. We're slightly over, but we're going to take just a couple more minutes, and then we'll hand you to the closing. I hope our audience is sticking with us just for a minute or two more. And I'd love to hear from the panelists just a closing thought to leave our audience with. Haisha, I'd love to come back to you to give your closing thought for this panel session.
Yeah, so just to summarize it in 1 or 2 sentences, I feel like now at the beginning of the second decade, it's a really interesting time. If we go back 2 decades, I think AVC or H.264 has been the king of the hill for a very, very long time. It's sort of like the position JPEG was in. And now I kind of feel like AV1 is a really good replacement, and it will probably be establishing itself for the foreseeable future. And we're still very early at the adoption of this. So I'm very, very excited to see how this will bring much improved compression efficiency and QoE going down forward.
Really cool. Thank you, Haisha. Tamar, I want to hand the microphone to you.
So I completely agree, and I want to reinforce Haisha's statement. I think we're seeing video workflows that are very demanding. I think we're at a tipping point where, exactly as you said, 264 is going to have to give way to more modern codecs. I think given the volume, the low latency, and the so many different areas where video is starting to be more used, not just video conferencing and streaming video. It really is in every single aspect of our lives. I think that hardware is inevitable. The switch over, at least to combined solutions with hardware, is inevitable. And as James mentioned, we're at a tipping point there, okay, where solutions are getting better, but we need to be able to offer a window into innovation, as Roberto said. And I think hybrid solutions like the one we've developed with NVIDIA and the APIs that they opened for us to be able to do that allow for innovation and, hybrid solutions that are software, hardware, moving to newer codecs, quality aware in the middle of all that. I think that's the only way we can really tackle the challenges that face the video at scale community that we've touched on here today.
Really insightful. Thank you, Timur. I'm going to head to James. How would you like to close the thoughts here?
Yeah, I mean, I don't think everyone here on the panel is certainly not going to stand still in terms of new innovation, but I think that a lot of the things we've been waiting for are sort of here, and they're accessible and they're affordable. So there's really not a big excuse to not be leveraging these new approaches and new techniques. And we've got standardization finally becoming a bit more solid in terms of low latency delivery, which is comparable to broadcast, and we've got all these great things we can bring to bear to deliver really rich solutions. And I'll just maybe quickly touch on one thing that we haven't sort of mentioned on this panel is, I'm personally, or we as a company are quite excited about the advances at the edge as well, in terms of, again, something that was just totally not possible 3 or 4 years ago in terms of the level of personalization that you can offer in terms of the video content and real-time manipulation of that. Not everyone's favorite topic, but novel, scalable ways to do DRM as well. They're all being really unlocked by the broad-based availability of edge compute that can manipulate quite rich video on the fly. So we're quite excited about what that brings as well.
Yeah, 100%. I'm conscious, as you say, we didn't talk to edge at this just due to lack of time, right? And it's a huge topic, and I think one that would definitely be addressed
Absolutely.
in future ones. Really looking forward to that. Roberto, I'm going to give you the final slot. Please finish our discussion.
All right, thanks. I think for me, my observation is that the journey is still ongoing. We're not done. We're probably not close to done. We've seen a continuous line of innovation, and what is different, I think, right now is that we're getting a little bit surprised by some of the innovation. The innovations that are coming out aren't all obvious, and I think part of that is the world has changed out from under us in ways that were hard to predict. We already know about the mobile stuff. Now we see the AI stuff. We know about codecs, but even today's new codecs are still based on some kind of old beliefs. One of the ways we can think about AI models are that they are a compression scheme. This is debatable, but that's one of the ways you can think about it. They're a compression scheme for probabilistic things. Well, that's video too, right? So what about the marriage of these things? Are we going to have much larger dictionaries that allow us to hallucinate what seems like higher quality content, perceptual quality as compared to PSNR quality, right? I think the answer is probably yes. So I think there are probably other beliefs that we have held for a long time that stemmed from the beginning of our experiences with the hardware that was available 20-something years ago that probably don't hold anymore. So I'm really excited about seeing how that's going to change and how we're going to go into the future from that.
Awesome. Thank you, Roberto. I want to extend our thanks to all of our panelists. Thank you so much for your time, for sharing your knowledge with this group. And I also want to thank our audience. Thank you for listening for us. I hope you learned a bunch. Feedback is a gift. Always don't hesitate to reach out. And yeah, have a lovely day. Thank you very much for your time, everyone. I'll hand it off. Thanks, guys.
Thank you so much for joining us for the 8th edition of Video at Scale. Thank you so much to all our speakers who put in so much effort and prepared this awesome content for Video at Scale 2023. We hope you enjoyed hearing about the advancement in the space as much as we loved organizing it. As a reminder, all videos from today will be posted on the AtScale conference website, the AtScale Facebook page, as well as the AtScale YouTube page in the next few days. See you next year in 2024.